Okay, so now what I want to do today is just do some more practice with the gas law stuff and the KMT stuff, and I want to show you what was on last year's AP exam. Okay, so from 2021. So sprinkled in there is going to be some review questions, some stuff that we've seen already from Unit 2 and maybe Unit 1. But for the most part, we're going to focus on 3-1 stuff and the 3-2 stuff. So kinetic molecular theory and the gas law stuff. So just to see how it looks on the AP exam. All right. So, whoops, let me go here. All right. So, so this first part of the question obviously doesn't have to do with Unit 3, but it's asking, is it a redox reaction? Justify your answer. And we could assign oxidation states. The hydrogen's going from +1 to 0. The carbon would be what? +2 over here and +4 over here. So the hydrogen's being reduced. +1 to 0, and the carbon's being oxidized +2 to +4. All right, so hopefully, we understand that this is a redox reaction. All right, so let's see if we got the answer right. Okay, so yeah, it is. Is it a redox reaction? Yes. H is reduced and carbon is oxidized. The oxidation state from hydrogen goes from +1 to 0, and the oxidation state from carbon goes from +2 to +4. So that's an easy 2-pointer right there. So that's nice, and that's just from last unit, so hopefully that's still fresh in your head. But let's go to the gas law question. All right, so if we look at part F, let me zoom in here. Okay, so this reaction's happening, and what we need to notice in this reaction is that it's aqueous going to two gases. All right, so at the start of the reaction, notice the pressure's 0, and that's because at the start of the reaction, all we have is this. It's not a gas. So no gases, so no pressure, no gas pressure. And so as the reaction proceeds, we produce hydrogen gas and we produce CO2 gas, and as more gas gets produced, obviously the pressure increases until we reach an equilibrium, okay, or until the reaction's stopped, right? And so the reaction's stopped, or we've reached equilibrium when we have 24 atmospheres of pressure, and that would be 24 atmospheres due to this gas, all right? So it says the reaction occurs in a rigid 4.3 liter container, so we know the volume. We know the pressure, 24 atmospheres. We know the volume, 4.3 liters. We know the temperature, 25 degrees Celsius, so 298 Kelvin. And the total pressure is monitored, as shown in the graph above. The vessel originally did not contain any gas, hence the fact that it had 0 pressure at time 0. Calculate the number of moles of CO2 gas produced in the reaction. Assume that the amount of CO2 gas dissolved in the solution is negligible. So CO2 sometimes does dissolve. Obviously, like you can have carbonated beverages and stuff. So CO2 does dissolve in water a little bit. So we're assuming that none of the CO2 dissolved. All right. So a couple things to look out for. Notice that this total pressure is not just the pressure due to CO2. It's due to the pressure of CO2 and H2. And what you really need to notice is that they are produced in a 1-to-1 ratio, 1-to-1. So that means this pressure, the 24 atmospheres, is half due to the hydrogen and half due to the CO2. So if we wanted to separate this into partial pressures, the partial pressure of hydrogen at this point would be 12 atmospheres, and the partial pressure of CO2 would be 12 atmospheres. If they had a different ratio, if they weren't 1-to-1, then you would have to multiply the total pressure by the ratio to figure out what their partial pressure is, okay? I'm gonna do it a slightly different way, and I'm gonna get the total moles of gas using the ideal gas law and then just divide by 2. Okay, because half of the moles are hydrogen and half of the moles are CO2, and what we wanna notice is that this question is asking for moles of CO2, right? So let's go and look at the work. All right, so This is just a quick ideal gas law, PV equals nRT. We're solving for moles of gas. So moles of gas equals PV over RT. 24 atmospheres was our total pressure. 4.3 was our volume. Okay. I underlined rigid there because it's a reminder that the volume is being held constant. Now, that doesn't really mean anything in this question, but a lot of times that is a clue that volume's remaining constant. Okay. So 25 atmospheres, 4.3 liters. Because our R value, or because our pressure is in atmospheres, this is our R value, 0.08206. And again, don't plug in 25 there. Make sure you plug in 298. And so when we solve, we get 4.22 moles of gas, but we have to remember that not all of that is CO2. That's the total moles of gas in the system. And because it's a 1-to-1 ratio, half of it's CO2 and half of it's hydrogen. So all we have to do is divide that by 2. And so we get 2.11 moles of CO2 for our final moles. And we probably should round that to 2.1 because 2 sig figs, 2 sig figs, 2 sig figs. So 2.1 would probably be a better answer. But they didn't tell us to worry about significant figures, so that's fine. All right. And that would only be worth 1 point probably, maybe 2 points, maybe 2 points. Like if this one's worth 2 points, then this one's probably only worth 1 point, the oxidation reduction one. So if this one's worth 2 points, it would be like 1 point for using the ideal gas law and then 1 point for realizing that you had to divide by 2 somewhere. So either plugging in 12 here instead of 24 or at the end dividing by 2. Either way, showing that you knew that the total pressure was not just the pressure of CO2, it was the pressure of CO2 and H2, all right? So there you go. Now, G is something we'll learn about in Unit 7, what a catalyst does, but a catalyst increases the reaction but is unchanged. So the answer to G would be after the reaction proceeds for several minutes, does the amount of catalyst increase, decrease, or remain the same? Justify your answer. It stays the same because the catalyst gets used, but then it gets produced again in the reaction mechanism. This is something, again, we'll learn about in Unit 7. So that one you wouldn't be responsible for just yet, okay? But, you might already know the definition of a catalyst, that it gets, that it's does not get consumed in a reaction. So it just stays the same, okay? All right, so that's maybe 1 point or 2 points. Whatever we're looking at 3 points from the last part of Unit 2 and the first part of Unit 3. So we're looking at 3 points there. And remember, it's only out of 46 points. And then if we go to question 7, this is a 4-part question, so a 4-point question. And it's all about KMT and gas laws, okay? And so that's going to be 7 total points. So 7 out of the 46 points came from 3-1 and 3-2 on last year's exam. Okay, 7 of the points, okay? We're looking at, 7 points from there. I think it was, 10 points from Unit 1 stuff? So we're looking at 17 points just from Unit 1 in 3.1 and 3.2. So, we're almost halfway there, okay, when it comes to the amount of material on here, all right? So anyway, let's look at this. So we got a movable piston. So what does that mean? It means it's not a rigid container. It means the volume's going to change. So volume can change. A student investigates the gas behavior using a rigid cylinder. The cylinder is rigid, but you can movable piston, okay? With a movable piston of negligible mass. So you're just not worried about the mass of the piston, okay? As shown in the diagram above. The cylinder contains 0.325 moles of oxygen gas, right? The cylinder has a volume of 7.95. It's at 25 degrees Celsius, it's at 1 atmosphere, and it asks us to calculate the density of the gas. Okay, so if you remember from our lesson, it's good to memorize the ideal gas law with density in the equation. So we know what density is. We know density is mass over volume. So if we can take our grams of oxygen gas and we can divide it by the volume, which is given right here, that will give us our grams per liter. That will be our density. All right, that's what we're trying to figure out. So one thing we could do is we could use PV equals nRT, solve for moles of O2, and then we would multiply by the molar mass of O2 to get grams, and then grams divided by this many liters would give us our density, okay? But this is a golden opportunity to use one of the shortcuts. And again, one of our shortcuts is memorizing the ideal gas law with density in the equation, okay? And so we could go right to solving for the density by plugging stuff in. So that's what I did. If we go to the answer key here, remember, pressure equals dRT over molar mass, density RT over molar mass. So if we replace this and solve for density, that means density equals pressure times molar mass over RT. All right, so our pressure was 1 atmosphere, molar mass of O2 is 32, our R value 0.08206 because the pressure we used was atmosphere, right? If that was millimeters of mercury or torr, we would use the 62.36 value for R. But because it's atmospheres, we're using 0.08206, and our temperature was 298. So when we solve, when you use this equation, the density units for this are grams per liter, and boom, we got our answer. Now again, we could have used PV equals nRT like we did back here, and we could have solved for N, and once we would got N, that would give us moles of the oxygen, and then we would multiply by the molar mass of the oxygen, and then divide by the volume in liters to get the density. Either way is fine, but this is a slight time saver. And remember, this is question 7, and it's the last question on the free response. At this point, you're probably running out of time, and a shortcut like this, even though it might save you 30 seconds, it might save you a minute, it's good to remember, okay? So that being said, it's only worth 1 point. Questions 4, 5, 6, and 7 are each worth a total of 4 points. And since this has 4 parts, you can assume, since the question 7 here has 4 parts, you can assume that each one is worth 1 point. Okay. So boom, we got our density. All right. So let's go back to the question. All right. So we're still talking about this setup here. Okay. Attempting to change the density of the O2, the student opens the valve on the side of the cylinder and pushes down on the piston to release some of the gas, and closes the valve again. The temperature of the gas remains constant. Will the action change the density of the gas remaining in the cylinder? Justify your answer. All right, so it's going to push some gas out, but what's going to happen to the volume? It's going to decrease. So yeah, you're going to get less mass, but you're also going to get less volume, and so the density is going to end up being the same. It's not going to work out it's not going to do the desired thing, whether the student wanted to change the density. All right, so let's go to the answer there. Okay, so no, volume and amount of gas are directly proportional. Okay, so moving the piston down to lower the volume while having the valve open will cause gas to escape, and the resulting contained gas will have the same density as before. Okay. So the other way to kind of explain that is, so the answer again is no, but you could say pushing the piston down will remove some of the gas, so the mass of the gas of the system will go down, but the volume will also be decreased by moving the piston down, so the density will remain the same. Okay, so that's 1 point. Pretty simple question there. All right, so let's keep going. Let's go to the next one. So again, we're talking about the same system. So part C, the student tries to change the density of O2 by cooling the cylinder to negative 55 degrees Celsius, which causes the volume of the gas to decrease. Using principles of kinetic molecular theory, explain why the volume of O2 decreases when the temperature decreases to negative 55. So this is just asking, why does volume and temperature have a direct relationship? As temperature goes down, why does volume go down? Okay. And you're going to say, lowering the temperature decreases the overall speed of the particles. The particles are going to collide less often with lower energy, and that's going to decrease the pressure. And because that's going to decrease the pressure, the piston is going to fall down, and that's going to decrease the volume of the gas. Okay? So let's see if we got that answer. Decreasing the temperature decreases the speed of the particles. So, and that should say they. So they will collide less often if the volume were to remain the same. However, to maintain a constant pressure, because we have a piston, the volume must decrease. So the force of the collisions per unit area remaining the force of the collisions per unit area remains constant. Okay? So decreasing the temperature decreases the speed of the particles, right? We know that. The average kinetic energy goes down, so the speed of the particles must decrease. So they're going to collide less often if the volume remain constant. But here we're maintaining a constant pressure, okay? Because we have a flexible container, because we have a movable piston. So pressure is remaining constant. So the volume must decrease, so the force of collisions per unit area remains constant, which is our measurement of pressure. Okay? So hopefully that makes sense to you. And let's go to the last one. It says, the student further cools the cylinder to negative 180 degrees Celsius and observes that the measured volume of oxygen is less, much smaller than the volume that is calculated using the ideal gas law. So O2 is deviating from the ideal gas law at negative 180 degrees Celsius. Assume all equipment is functioning properly. Explain why the measured value of oxygen gas is smaller than the calculated volume. And they give us a note. The boiling point of oxygen is negative 183. So we didn't cool it all the way down to negative 183, but we got it close. Okay, and so negative 180, that's a really cold temperature. Okay, so why do gases start to deviate from ideal behavior at low temperatures, right? So we should already know the answer. So let's go see what we got. All right. So what, I kind of switched this up. I would say, it says the slower the gas particles move, the lower the temperature. I would say the lower the temperature, the slower the gas particles move. I don't know why I switched that. So the lower the temperature, the slower the gas particles move, the less IMFs can be ignored. So the slower the gas particles move, the less IMFs can be ignored. So remember, an ideal gas ignores intermolecular forces between the particles. But the slower the particles move, so the lower the temperature, the less you can ignore IMFs. Because the particles are moving so slow at this temperature, the weak London dispersion forces, so I wanted to get kind of particular with the IMFs that oxygen have. It's a nonpolar molecule, so all it has is London dispersion. So the weak London dispersion forces of oxygen turn on, kick in, however you want to say it, start to attract each other, and the gas ends up occupying less volume because now the particles are actually attracted to each other, and so they pull closer together than what would be predicted based on the ideal gas law if we ignored those IMFs. Okay? So remember, this is not about particle volume. If this had been a very high pressure and oxygen wasn't behaving according to the ideal gas law, then you would say because you can't ignore the particle volume anymore. But because we're talking about low temperature, why do gases deviate from ideal conditions? It's because at the lower the temperature, the more inelastic their collisions become, the more intermolecular forces start to come into play. And so if the oxygen molecules start to stick together a little bit, they're obviously going to occupy less space than what's predicted if they wouldn't stick together at all. Okay, so we're getting we're getting very close to the point of condensation, and so that would mean some of these oxygen molecules are going to start sticking together due to their London dispersion forces, and that is not behaving like an ideal gas. Okay, so that's four points there for question 7. So a little bit of writing there to do. You don't need to overdo it. What I wrote there for the answers, it would be sufficient enough. I think the main thing is that time saver. Here, we used it. We don't always use it. It's not always something that's used. But I would say we don't always use it in the free response. I would say knowing the density ideal gas law equation saves you time at one point during the test, either on the free response, but more often than not, it'll be maybe a multiple choice question where knowing this might save you time, or knowing this will make the math a lot easier. So that'll save some time. And remember, on the multiple choice, you don't get a calculator. So anyway, hopefully that helps you out and helps you understand 3-1 and 3.